Section 4.8, graphs and derivatives of implicit relations. Our objective is to find the derivative of y with respect to x. We've talked about this just a little bit already. When we're given an implicit relation as opposed to an explicit relation. Y'all didn't realize that there was a difference, but as we get into this, I think you'll be able to see the difference. An explicit relation is an equation in which y equals some function of x, such as y equals x minus tan x. Your y is on a side by itself. I can take the derivative dy dx over here and take the derivative on the right hand side without any problem. 1 minus secant squared x. Done. All there is to it. But an implicit relation, that's a whole different deal. Okay? On an implicit, sorry, that kind of covered that up to where it didn't look very good. On an implicit relation, it's an equation in which both x and y appear on the same side sometimes. They might be split, but they may be on the same side. Okay, like this right here, x squared plus y squared equals 9. And hopefully, if we think about this, x squared plus y squared equals 9 is the equation of a circle, right? Right? Which should also remind us, if you're thinking about it, that's a circle with a radius of 3. Okay, looks something like that. That's why we've got here an implicit relation. These may or may not be functions. Okay, a circle is not a function. So we're talking about relations here as opposed to the functions that we've been dealing with. This right here would be a function. This other one, not necessarily. Okay. For implicit differentiation, to find dy dx for a relation whose equation is written implicitly, we want to differentiate both sides of the equation with respect to x. Obey the chain rule by multiplying by dy dx each time that you differentiate an expression that contains a y. Now again, we talked about this already, but this is a big thing right here. You want to put that dy dx every time that you differentiate an expression that has y. Then you want to isolate the dy dx, get all of your dy dx terms on the left side or on one side of the equation, and all of the others onto the other side. Factor if you need to. Divide both sides by the coefficient of dy dx so that you can have your final equation there. These equations should always end up in the form dy dx equals, just like the ones you're used to, but it's going to take a little bit longer to get there. Okay, so let's dig in and try to do one of these instead of just talking about it. 5x squared plus y squared equals 25. This equation describes what shape? Well, we've already done that. We looked at x squared plus y squared equals 9. This is a circle with radius what? Hopefully you knew 5. Radius of 5. X squared plus y squared equals 25. It is centered at the origin. Why? Because there's not x minus a number or y plus or minus a number. So centered at 0, 0. All right, when it says differentiate implicitly, and we talked about this, x and y are on the same side, so you go through and take the derivative, just like you normally take a derivative. The derivative of x squared is going to give me 2x plus derivative of y squared, that is just 2y, but because I am taking the derivative with respect to x, that's where we put that dy dx. Equals, derivative of 25 is 0. Okay. Pretty easy thing. I saw y in my problem. I was taking the derivative with respect to x. Therefore, I had to take my derivative, or I had to put the dy dx there to symbolize that that was what I was doing. Now then, go through. I want to get dy dx by itself. Okay. So I need to do 2y dy dx equals negative 2x. and divide both sides by 2y, and dy dx will be negative x over y. Okay. Now then the next part says calculate the two values of y when x equals 3. Okay. I should say, let me go back for just a moment. This equation right here, this is still the slope of your tangent line. Okay, it didn't change because we were graphing this or differentiating it implicitly. This is still going to give you the slope of your tangent line. So let's find these two values of y when x is 3, and then we'll be able to see that. Two values of y when x equals 3, so you go back up to your original and you have x squared. Sorry, when x equals 3, how about if we put in 3 squared plus y squared equals 25. Okay, so y squared is going to be 25 minus 9, which is 16. And so your y value then is plus or minus 4. Okay, those are your two y values when x is 3. You've got an ordered pair 3, 4. And you've got an ordered pair 3, negative 4, where you will have tangent lines. That's what we're fixing to get to. Okay, those are 2 points, both of them on that circle. We want to draw a line with the slope dy dx through the point found in part 3 with the lower value of y. And then we want to figure out how this line is related to the graph. Well, I've kind of already given that away to you, but let's get down here and get this thing drawn. So I'm going to make my graph. I'm going to go out 1, 2, 3, 4, 5 in every direction. 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So circle. And I hope it is somewhat, probably not, circular. Okay, it said use the lower value of y. That's the 3, negative 4. So if I go over 3 and down 4, that is about that point right there. Okay. Slope dy dx. All right, well, dy dx equals negative x over y. So that is going to be, in this case, negative 3 over my lower value of y was a negative 4. So my slope is 3/4. So from that point, if I rise 3 and run 4 and draw a line, I have this really nice tangent line running right through that point. Okay. That line is related to the graph in that it is the tangent line. Okay. I could also have a tangent line up at the point 3, 4, over 3, up 4, right in here. I could have a tangent line there as well. That is not the one that it asked me for, but I could certainly have that line without any problem. Okay. So writing an equation of this one that it gave me right here. Here is my slope. My ordered pair is 3, negative 4. And so my equation is y equals 3/4 times x minus 3 minus 4. There's the equation of your tangent line. So this is pretty easy stuff, not a big deal. Oh, and then we look at this one. Okay, well, let's find dy dx. Get this one done. This is our last example because this is all there is for right now. We'll do some more the next class period, but this is all there is for right now. Okay, go through and you have to differentiate every single term. This one right here is going to be one where I need dy dx. This one right here, don't forget that those things are multiplied. You've got to do your product rule. Okay, don't forget the product rule on that one right there. This one right here is normal. We can deal with that. I don't have any strange letters running around. And that's going to be the derivative of a constant. Okay, so going through here, I have 4y cubed dy dx, because I'm taking care with respect to x, and I did not have an x there. So by the chain rule, that's dy dx. Plus, this next one, I've got to do product rule first, times the derivative of the second. plus the second times the derivative of the first, which will be 3x squared, and I'm taking derivative with respect to x, so I don't have anything else there. The x dx just goes to 1. Minus derivative of 2x to the 7th is 14x to the 6th equals 0. Okay, this is kind of messy looking. Let's get it a little bit neater, and then let's get some things rearranged on different sides. Dy dx plus 5x cubed y to the 4th dy dx plus 3x squared y to the 5th minus 14x to the 6th equals 0. Well, these two terms right here have dy dx in them, so they're going to stay on the left-hand side. These two terms right here without the dy dx are going to be moving to the other side. When I'll just do 2 steps. So we got 4y cubed dy dx plus 5x cubed y to the 4th dy dx equals 14x to the 6th minus 3x squared y to the 5th. No problem. Dy dx is in common on the left-hand side. Factor that out. We are almost there, y'all, and this has been relatively painless. Times 4y cubed plus 5x cubed y to the 4th. Close it up. Equals your 14x to the 6th minus 3x squared y to the 5th. Alright, divide both sides by this term right here, since it's multiplied by dy dx, and your dy dx final answer is 14x to the 6th minus 3x squared y to the 5th all over 4y cubed plus 5x cubed y to the 4th. And believe it or not, if I had an ordered pair here, I could plug in my x and y, and that would be the slope of the tangent line at that point on the function that you started with. So, not too bad as far as going through it. Still has a lot of work to be done if you want to find that, but it's a pretty good problem, and it's a nice thing to be able to do. All right, there's going to be the homework. So have a great evening. See y'all tomorrow at school. Bye.